This is Jeff Scott of Blackhawk Technical College. Yesterday, which was Wednesday the 20th of August, for whatever reason, I gave the lecture on Chapter 8 and thought that I had the recorder on, but evidently I did not. So I'm going to go back over that. There's just a few general things I'd like to talk about. And then afterwards, I'm going to switch over to the virtual desktop and go over a couple more C programs. The plan next week, just so you know, because some of you either permanently or maybe for a while are watching the tapes online, so just so you know that the plan this week was to go through chapters 1 through 8 and some C examples. The plan for next week is to go over chapters 9, 10, and 11. We're slowing it down a little bit because this stuff has all been basic, but chapter 9 is on structures, which are also known as records. Then we're going to go over chapter 10, which are character strings, then chapter 11, which are pointers. And then probably after that, I don't know if we'll get through all of that in one period or not, but I think we will. And then Wednesday of next week, the 27th, we will be going over a lot of examples of structures and character strings and pointers. And then the week after that, of course, we don't meet Monday because it is Labor Day. That'll be the 1st. But when we come back on the 3rd, you will probably have the 3rd and then the entire next week, 3 straight classes of labs where I'll give you probably 3 programs. Then when we get done with that, so that'll get us through 4 weeks. When we come back the next week, between Monday and Wednesday, and I don't even know when that is, like the 15th or whatever, we're going to go over the rest of the book, which are chapters 12 through 19. And you may not even get any homework on that after that, I don't know. But ideally, like I've said in the past, but somewhere within 5 or so weeks, I want to be done with the C part, and we're going to jump right into Objective C and look at the other book, spending probably more time on Objective C because that's literally a new language. And then whatever time is left, we're going to jump in and look at Swift, which is Apple's new language for development. So chapter 18 starts, or chapter 8 I should say, starts on page 119, and I'm going to just be jumping around as I have been in here. So the next page here, page 119, at the top of the page, the that's interesting. Okay, no, I guess I wanted 20. The author says here things that you should know about functions. Well, again, when you look here, who can call it? The type of value it returns. So if we look here, it doesn't return anything, right? It's of type void. The function name, it's print message. And the arguments it takes. Again, it takes none, so it's got void. All right? This should all make sense to everyone in here. Now, I just want to mention something. I said this yesterday in class, and I'm saying it again because I'm trying to be complete here. See why I hate CourseSmart and this copy tool, because it does no formatting for me. So, all right. So yeah, that's lovely. So I throw this in here. So again, take me a second just to fix this and also to format it just minimally. So again, what the author is saying right here, and I apologize for not having this done ahead of time. I guess I thought it would come out a little better than this, so but it doesn't. All right, that looks not bad. Looks even better. All right, what I want you to get out of this little bit of a program snippet here, the way that this program is written is just fine. But notice that there's main, and the function above main does not return a value. Okay? By default in C, functions that return values, C thinks that they're all integers. Why am I telling you this? Because if we did this, if I took this function right here and moved it down here, the program would not work, because I've defined a function that doesn't return an int, and I've defined it after main. So how would I fix that? If I wanted to do it like this, if I really wanted to do it in this way, I'd have to either, well, not either. I'd have to basically set up a prototype for the function, like this. So if you have main at the top of your program, and by and large most programmers do, you do what's called prototype your functions. So what you're saying is, hey, hey main, someplace later on in the program, I've got a function named print message that does not return a value and does not require any values. But some programmers say, no, just the way to get around that is just take main and just put it at the very bottom, because if you put it at the very bottom, then you don't even need that. Well, I say that even if you're going to put main at the bottom, it's a good idea to prototype these functions like I've shown you anyway. So I prefer you had main at the top. If you don't want to do that, that's fine, but I do want you to do a prototype like you see in gray here. Questions on that? If there are any, get a hold of me and let me know, okay? All right. Now, any time you define inside of, so let's say that inside of print message here I defined a variable, and I said int age equals 50. All right, so programming is fun, \n. So I'm going to just put another line here. I'm just adding to the function. Especially if you are under %d years old, \n, age. Okay? So this will come back and it'll say programming is fun, especially if you are under 50 years old. Why am I telling you that? Because by default, variables that you declare inside of functions, and that's all main is too, is a function, they're automatically auto. Oops. They're auto variables. What that means is you don't put this in here, but that's the default. And all that means literally is this variable called age comes to life when it's defined, and it goes out of existence when the curly brace is there. So they mention this in the book on page 124, and let me pop back to the book for a second. Do that over here. Okay. So again, jumping to 126 here. Early in the morning, it's 6:30, and I guess I'm not as awake as I thought I was. There's more on the function prototype declaration that I just mentioned to you, so if you want that, it's on the top of 124. But here's what the author says. Variables defined inside of a function are known as automatic variables because they're automatically created when the function's called, and their values are local to the function. So they're local variables that get into scope when they're declared and go out of scope when the function ends. One thing I did mention to the class yesterday, and since I didn't tape it, I want to make sure I put this in here so people understand this. All right, let's show this the way that I recommended that you do it here. So in other words, here's main. Main calls print message. Okay. So again, int. We'll do this inside of main. Okay, and we'll say int age equals 50, just like I did before, and we'll call print message and we'll pass to it age. And let's say that for whatever reason, this is nice, this twice. Fix this, sorry. Alright, so let's say that we do define a variable, which again would be auto, but we don't have to say that because it's the default. But we say int age equals 50. Now we're going to call print message and we're going to pass it in age. All right, so this will have to change to int age. But let's assume for a second that what we want to do is this thing that says, especially if you're under that number of age, we want to have that be in a different function. Right? It's kind of a silly example, but just so you get this, there's a reason for me showing you this. I'm not trying to waste my time or yours. So we're going to say void print message 2 int age. Like I said, just hold on for just a minute if you don't mind, and hopefully this will make some sense then. So I'm going to have to call it here. print message 2, and we're going to pass in H. What I'm trying to get across to you is if you look at the way this program works, I'm going to have to also prototype that function now. Alright. Main has a variable that's called H. Okay? It's in scope right now. Then what happens is it calls print message and it passes H. So what happens literally in the computer is there's a place called the stack, which is an area of memory, and it grabs all the variables that currently exist and kind of takes a snapshot right now because it's about to give up control of the system from main and give it the print message. Alright, so it's got its own copy of age, and then it makes a copy of that and passes that over to print message. So now print message is in control, and it writes out programming is fun. Age was passed into that, and it takes and passes age to yet another function. That function, print message 2, then prints out, especially if you're under 50 years old. The output is identical to what you saw before, but what I'm trying to show you is we've got a function that calls a function that calls a function. And as far as the way that works in here, you have to make a copy of all this stuff and throw it on the stack. Then you make a copy of all this stuff and throw it on the stack. Even if it's the same stuff that we had here, it's its own copy. Then we make a copy of all this stuff and throw it on the stack. Then when it hits that curly brace, control goes back to here and it says, oh, there's no more code because it hits the curly brace again. Then it jumps back to here. Then it returns 0 and it's done. So many programs, the way that they work is you have a routine that calls a routine that calls a routine, etc. And there might be a lot of those before something happens. And that's all I'm trying to kind of simulate right here. We also got into a little bit of a talk yesterday because I mentioned stack. And stacks kind of work the way that the trays in the Blackhawk Technical College cafeteria work. So if the cafeteria worker comes in and he or she pushes down on their little spring mechanism there and puts 50 trays in, most people will grab the top one and use that. In other words, the last tray that was in is the first one that's used. Now, granted, you know, it could be dirty and whatever, but that doesn't really matter in this example. All right, and so that is referred to as a last in, first out, or LIFO type of structure. That's an example of a data structure. Another example of a data structure is something called a queue, and that's like the line that you have, I don't know, at the bookstore, for example. So if there's 3 people in line at the bookstore, the first one in line is the first one it's served. So unlike a stack, which is last in, first out, a queue is first in, first out. And there are other things. There are linked lists, and there's other different types of data structures that you can work with, etc. All right. So in your book on 131, they sort of get into this stuff that I just mentioned to you. Notice functions, calling, etc. So there is no limit, you know, as far as how many functions can call, how many other functions, etc. All right, turning up to page 134. All right, it says here, when a call is made to a function, the compiler assumes the function returns a value of type int unless you do one of the following. This is what we talked about before. Unless you define the function before main, or before it's called, or you prototyped it, or both. All right? So we've already kind of talked that out, so I hopefully everybody has an understanding of that. If for some reason you don't, just let me know. I'm glad to work with you on it. They give you a couple little final things here, some final reminders and suggestions regarding functions. Again, by default, the compiler assumes, unless told otherwise, that you're returning an int. When you define a function that returns an int, say it does anyway. Even though technically you can leave the word int off, don't do that. When defining a function that doesn't return anything, put void in there. Whether it's the return type or whether it's the parameters. You know, a lot of people always do that. They put void even inside of the parentheses. The compiler converts your arguments to agree with the ones it expects only if you have previously defined or declared the function. Again, prototype. So to be safe, prototype. Now there's some really good code or stuff in the book here on 137. This whole section here on top-down programming, I'm not going to go over any of it because it's stuff that I talked about with you back in the days of JavaScript. When we talked about grabbing a, going and taking a program and breaking it down into pieces and breaking those pieces down into pieces, etc. Again, kind of the act of writing an outline, so to speak. But here we're talking about top-down programming, all right, going from the very general to the very specific. And when we're breaking it down into groups of functions. Okay? So there's a little bit more on that in there, and they probably do a better job than I just did of explaining it to you, but it's pretty good. Global variables, just so you know the way that global variables are set up in here, if I define a variable at the top of my program, so I define it before any function, so if I say here int age equals 50, then technically I don't, of course I wouldn't define age here. I don't even have to pass it here, so I don't need it here, or here, or here. Why? Because if it's defined outside of any function that's in the program, it's considered global to the program. Now, it's even possible that other programs may be able to use this variable, and that's not very well done. Now, if I had another program in here, another C program, not with another main, but with another function. So if I created another program, all right, and that was, so pound include stdio.h, all right, and I'm going to come in here and I'm going to say int, we'll make it a void print age again. Kind of stupid, but just so you see this. Printf that age again was %d \n. Remember that %d is just, this is a placeholder. That's called a format specifier, and it's holding the value of the variable age. All right. Now, as the way that this program is written right now, it won't work because because age is defined in a different file. But what if I wanted to use that in here? Can I? And the answer is yes. But then I have to say extern int age, which means that age has been defined someplace else, and as long as, in this case, as it's in the same folder or the same area as this program, the system will go out and find it. All right. Now, what if I don't want that to happen? What if I don't want you to be able to use this age in any other routine, in any other file other than this one? Then I can put the word static in front of it, and that keeps that from happening. You also use static, as we talked about before, so something retains its value. And so this is not a good example right here. But what if I was going to do this, that every single time I ran this program, so in main, I was going to put in here, I was going to create a variable, int, we're going to call this print message counter. All right? And it's kind of a stupid example, but just so you see it, equals 0. All right? So now when I call print message, I'm going to pass to that print message counter. All right? And that print message counter that you see right there, now what I want to do is every time I run this print routine right there, I want to add one to my print message counter. Okay? The problem with the way this is written right now is every time it comes into main, it's going to create a new one of these. It's not going to remember its old value. If I want it to remember its old value, I can again put static in front of it like that. All right? And the last thing is, let's pretend for just a second, this is a silly example what I'm about to show you. All right? This is a silly example. Well, let's suppose I was going to write a for loop, and I was going to say int I equals 1. In fact, we're not going to make it an int. We're going to make it a special kind of int, a long int, which can be like a gazillion, whatever that is. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm going to print that out like 10 million or a billion times. I'm going to call this, which is really silly to do, but just so you get the idea. All right. So this print statement, I'm going to end up calling it that many times. What I can do is this can slow down processing. If you've got something that's looping or whatever that many times, it can really slow down a program. So what I can do is when I create this variable right here, I can put in front of it the word register. What that means is try to use one of the special register locations that exist in memory very close to the CPU, which can speed up program development. So we talked about today auto variables, static variables, and now we're talking about register variables. The problem with register variables is the system can turn around, and even though you request a register variable, it can deny the request because it uses a lot of the register variables for its own internal stuff, and there's only a limited number. It's like 2 or 4 or 5 or something like that that the system even has available anyway. If you ask for this and there is no register available, it's as though you did this, the default. All right, so it doesn't hurt to do it, but I'm just saying you may not get it what you think you're going to get. And if you want a little bit more on that, if you turn up to page 156, you'll notice on 156 they talk about automatic and static variables. All right, so you may have noticed that when I'm doing this, and that's it for the chapter, when I'm going through this like that, I'm not reading stuff out of the book to you because I think that's a waste of both our time. Okay? So let me jump over to the virtual desktop side now, and this is what we went over. 1, 2, 3, 4, 5, 6, 7 programs quickly. So that's what I'm going to do with you. It's going to be a little smaller, and just so you know, and this is particularly for someone like you, Mike, who's going to be watching these tapes, the tapes are now all of them except for the one I'm taping now, of course, and one that I've got to fix some audio on. Everything else is out there for all my other classes, but I'm using YouTube this year because I don't have a server to use anymore, and it appears as though the resolution is a little worse on YouTube. Sorry about that in advance. So we don't care that much about these comments. Write a C program that inputs three integers from the keyboard and prints the sum, average, product, smallest and largest of those numbers. Okay, I'm going to make that a little bigger so we can see this. So there's our 3 numbers, our sum, our product, our minimum, our maximum, and our average. Some of this should be pretty simple. By now, hopefully, you understand this. All right, this is telling us to read in 3 different integers. Again, we're going to get into this ampersand and its counterpart, the asterisk, next week when we talk about pointers. But this just says, at the address of the memory location that holds num1, put that digit, or that integer. At the address of the memory location that's called num2, put that integer. At the address of the memory location that is called or holds num3, put that integer. Once you've read in 3 integers, add the 3 up and that becomes the sum, multiply the 3 one by the other, and that becomes the product. This program is not well written because right now what you're doing is you're taking sum, which is an int, and dividing it by 3, which is an int, and then you're putting it into a double. So it's going to do truncation because it'll do the math first, truncate, and then assign it. So I really should have either said double, in other words, I should have cast that, or I should have said divided by 3.0, or if I'm really anal and want to be serious, I could have done them both. But I should have done one or both of those. I didn't. All right, so how are we finding the smallest number? Well, again, assume for a second that we've got these 3 numbers, and these numbers are 45, 91, and -3. You and I can look at it and know the smallest one's -3, but what are we doing here? We're assuming the first one is the smallest. Then we're comparing the first and the second. So we're comparing 45 and 91. If it's less, it's not, but we swap them basically. All right? And then we compare the last one. So if you look at it this way, what we're doing in here is we're saying, okay, min. We're initially setting min to 45. Then we compare 45 and 91. So min is still 45. Then we compare 45 and -3. So min now becomes what will be its final value, which is, of course, -3. All right. In much the same way, when we're doing this, we also have max, which again, when we first start, max is 45. So we compare max, which is in num1, to num2, which is 91. So max gets reset to 91. Then we compare that to -3, and it's still 91. So when we're done, min holds -3, max holds 91. All right? I mean, I've gone through the whole program with you. Then we just print them out. So that was the first one. Sure. Then we've got a palindrome. It's a numeric palindrome. It's something that reads the same forward and backward. So for instance, looking at that one, that's a numeric palindrome because 18181 is the same forward and backwards. 1, 2, 3, 4, 5, 6, of course, isn't. So the first thing we want to do here is we want to count and make sure that you have 5 digits. So in other words, if I put in this, it's illegal because I don't have enough digits, and if I put in this, it's illegal because I put in too many digits. So the first thing that we're going to do here, all right, notice I prototyped. It's called return number of digits. So I prototyped because I listed it after main. And what are we doing here? We're counting, and we're returning the number of digits. That's what gets returned into count. And we use that, and we check, and if it's not equal to 5, we just give you an error message that says number must have exactly 5 digits. Then in this else, what we're doing right here is we're picking off each individual digit. So when we get done with this code that you see in gray here, lines 47 to 55, we now have converted 181 to 1, 8, 1, 8, 1. And this becomes first digit, second digit, third digit, fourth digit, and fifth digit. Then we simply use an if statement that compares the first and the last to make sure they're equal, and it compares the second and the fourth to make sure they're equal. The number you put here is irrelevant. And if the first and last are equal, and the second and the fourth are equal, it's a numeric palindrome. Whereas again, in this one, as you can easily tell, it's not. All right? So that's what we're doing here. Comparing the first and the, you got the first and the fifth and the second and fourth have to be the same. If they are, it is a numeric palindrome. Otherwise, it's not. And I tried to put sample runs up here too, so you can see what's going on. All right. Multiple, very small, very simple, crisp little program that says input 2 numbers. All right. This says does 5 go into 777 equally? It doesn't, so it's not a multiple. This says does 11 go into 88? Evenly. It does, so 88 is a multiple of 11. It should be by a factor of 8. All right. Sorry about that. So all we do is we read in the 2 numbers, and then we check and say, can the first one be evenly divided by the second one? If it can, it is a multiple. Otherwise, it's not. That's it. I guess this does say 88. So it's not in here. The next one is your typical miles per gallon programs. So you want to be able to enter in a miles per gallon or -1 to end, then enter in a number of gallons driven, or miles driven rather, divide the miles driven by the gallons used, and you get your miles per gallon. You'll notice here that when you do this, by default, C usually, if you don't do any formatting, it usually breaks something down into 6 decimal digits. All right. So we do it a few times. Then we eventually put in -1, so I should have really added that. So we put in -1 to end the program. All right, and boom, we're done. So what do we have here? There's our stop value, so we're using a constant. They do show another way you can use constants in the one of the chapters we went over today. Do it this way. This will work in all versions of C. The other one may not. So we've got miles driven, gallons used, total miles driven, total gallons used, miles per gallon, and total miles per gallon. One thing to realize is the total miles per gallon is not calculated until the very end of the program. All of the other values are either calculated or incremented, etc., inside of the loop. So we tell them first, this is our priming read that says enter gallons used. If they put in a -1, he'll jump right down to here. And that's another reason you should always initialize your variables. Remember, if I left this off, so if I just said this, if I just did that float miles driven, all right, then I've not initialized that variable. In some programming languages, and C is not one of them, it'll initialize it to 0 for you, but C does not. So we add to our total gallons used after we read it in, then we enter the miles driven, and we add that to the total miles driven. To get the current miles per gallon, we divide miles driven by gallons used and print that out. Then we ask them to do it again. All right, if we have not put in -1 here, we'll go down, so then we put in gallons used, we do it again with miles driven, etc. Eventually, hopefully, we put in -1 to end, then we do our total. That's that program. Then I did a gross pay program. All right, here's our maximum number of hours you can work without overtime, our overtime rate. Here's our variables, hours worked, hourly rate, gross pay, and total gross pay. So again, our priming read for hours worked, as long as we didn't enter -1, then we enter the hourly rate. Check here for overtime. Did they work less than or equal to 40 hours? So that's straight time. Otherwise, they've got overtime coming. Make it a little easier for you to see here. All right. And add that to your total gross pay. And then finally, ask them to enter hours worked again. Eventually, they'll put in a -1 up here, which will stop the program, and then you'll print out just the total gross pay when you get all done. That's that program. I didn't run any of these in class either, just so you know. This is the one I might assign for you. All right, we'll see. But, in fact, let me run this one, so you can see that one in action, so to speak. And there may have been an error in this program, but I think that for some reason I goofed up, and when the program ends, my check was wrong. So that's on me, but that's okay. We'll look at it anyway. Okay, this was called C programs. Oops, CD to C programs. It's company pay. CL company pay. It can be either way. That's C. All right. So company pay. So you enter a 1. That means that the person is a manager. All right. Enter their salary, $1,000. Okay. You enter a 2. They're an hourly worker. Enter the hours worked, 50. The hourly rate, 10. So they did get overtime. Put in a 3. Commission worker. Notice I've got check there for greater than 0, -4. Doesn't take it. Illegal sales entered. It asks you to do it again. So 3 again. Let's say they made $9,000. So now they made $763, and that's $250 a week, which is their base. Plus, I think it's either 5 or 6 or 7 or something like that percentage of their sales. So that's the percentage of 9,000. Finally, you've got your commission worker. I'm sorry, your piece worker. Again, if we put in a bad number of pieces, right? Well, I guess I didn't check it. I thought I did. So we'll put in here -4. All right, no, this is illegal. So number 4, and we put in, they made 10 pieces, and they get $100 per piece. So they make $1,000. This I don't think is working right now. It did work good. All right. So that's the number of employees that I went through. 1 manager, 1 hourly worker, 2 commission workers because I put in the illegal input, and 2 piece workers, again, because I put in the illegal input. That's probably the one that I'll end up assigning for you, so I, of course, am not going to go over that one. Alrighty. And then finally, this calendar is the one that I did, and I went over it in a different lecture, so that one will be out there if it's not already. So that one looks like this. It asks you to enter a year, so the current year, 2014, and it gives you a calendar, simple calendar for that year. So again, we're in August. Today is Thursday, August 21st, and you can see that. All right, so for example, you can tell that Labor Day is the 1st. If we looked, Thanksgiving is the 27th. Christmas Eve will be a Wednesday. Christmas Day will be a Thursday. New Year's Eve will be a Wednesday, etc. All right, so that's it for the chapter, and I guess I'm done.